Hi everyone, welcome back to this video. Radical Tutor here explaining. In this video, we are going to look at meso compounds. What are these meso compounds? So meso compounds are simply compounds that have internal Miller plane. So compounds that have got internal Miller plane are said to be meso compounds. So if you don't want to say that these are compounds that have internal Miller plane, you can simply say that these are compounds that have a line of symmetry. So any compound that has got a line of symmetry, that compound, that internal line, that line should be inside. So if you have any compound that has got internal line of symmetry or internal Miller plane, then that compound is said to be a meso compound. So for instance, I'm going to give you examples of compounds that have got an internal Miller plane. And mostly what you're supposed to know is that meso compounds, these compounds, they should always have, two chiral centers. So you should have chiral centers. What is a chiral center? A chiral center is actually a carbon. So mostly it's a carbon, or it's a, let me just say an atom that has four different atoms attached to that carbon. So we can have hydrogen, we can have chlorine, we can have bromine, we can have maybe sulfur, like that. So this carbon has got four atoms surrounding it, meaning that it is termed as a chiral center. Now, if you also have another chiral carbon like this, we have a carbon here, we have also hydrogen, we have also okay, we have a hydrogen, we have a chlorine there, then we also have a Br, you have also a Br here, and also you have a sulfur. So we are saying that this compound is going to be termed as a meso compound because it is having a Miller plane. So a Miller plane is where if you are to cut this into two equal halves, if you are to draw a line of symmetry there, you are going to find that if you get this part of the molecule of this chiral center, flipping it onto the other part, if you are to flip it onto this other one, you are going to find that it is going to flip equally onto the other part without any other space left. So that is what we call as a meso compound. So this compound is going to be called a meso compound because on each chiral center, or in other words, this chiral center has got the same constituents as this other one. So if two chiral centers have got two have got the same constituents, then you can easily draw a line of symmetry on that particular compound given to you. And once you do so, then that compound is termed to be a meso compound. So a meso compound is any compound that has got that Miller plane, or that internal Miller plane like that, or that line of symmetry. All right. Having laid that foundation, let's look at some more examples and see how we can identify these meso compounds. So with me here, I have this example here. Let's see this example. Can these be meso compounds or not? So this compound here, this first one, is a meso compound. Why is it a meso compound? It is a meso compound because you can easily draw a line of symmetry. So you can draw that line of symmetry like that, meaning that this side of the molecule or of the compound can flip onto the other side equally without any space left. So because this chlorine can come flip onto the other fluorine, the hydrogens can flip onto the other hydrogens, these can flip there, meaning that these can flip equally without any space left. So that means this compound is said to be a meso compound. So this one is a meso compound. So this one is a meso compound because it has that internal Miller plane, or it has that line of symmetry like that. Then coming to this other one, which is number 2, this also is a meso compound because you just identify if you're able to draw a line of symmetry. Are you able to do that? Yes. So if you're able to draw that line of symmetry, meaning that each molecule or each atom can flip onto the other atom without any problems or any space left. So in this case, this can flip on this can flip on that can flip on this can flip on that, and you are going to have that compound as a meso compound. So this one also is going to be a meso compound. So this one is a meso compound because it has that internal meaning that inside the line of symmetry, you are able to draw this inside this inner inner plane image, in other words, or that a line which is inside that particular compound given to you. And once you do so, identify if what is this side is equal to this side, then you are going to simply say that that particular compound given to you is a meso compound. All right, that's how you can identify. So in other words, what you can simply say is that these meso compounds have got what we call as the mirror plane. So by mirror we say, if you draw a line here, what is this side is going to face what is exactly on this other side, or reflect what is exactly on this other side, but the same. So such that if you are to flip them, they are going to align each other equally, and hence you call that particular compound as a meso compound. All right, coming to this other one here, which is 3, let's check, can this compound be termed as a meso compound? Yes, this compound is a meso compound. Let's see. This hydrogen here is, remember here I've used the wedged bond and the dashed bond. This wedged bond in chemistry simply means that this particular atom is pointing at you, while this dashed bond, whenever you see the dashed bond here, meaning that that particular atom is pointing away from you. So this is pointing at you, this one is pointing away from you. Now let's see, this bromine which is pointing at you, on this side it's also pointing at you. The hydrogen which is pointing away from you, this side also it is pointing away from you. That means you can easily draw a line of symmetry on this particular molecule, because you have two chiral centers. Okay, you have two chiral centers which qualifies this particular compound to be a meso compound, and then you can also draw a line of symmetry there. So if you are to draw a line of symmetry here, meaning that this side of a molecule can actually flip onto the other molecule equally in that order. That means we've drawn the line of symmetry, the internal line of symmetry, or the internal mirror plane, and therefore this also is going to be said that it is a meso compound. So this one is a meso compound like that. It is a meso compound. So you should make sure that if you have chiral centers, what is at this chiral center is actually the same with what is on that other chiral center, and the attachments should be the same. Also, the arrangement of those atoms should be in the same direction. But if one is in a different direction, then you cannot have that molecule to be a chiral center. Sorry, you cannot have that molecule to be a meso compound. Okay, so that's how you identify that this particular compound is a meso compound. Now let's go to this one. Let's look at this one. Are we able to draw a line of symmetry on this molecule here? So if you look at this molecule, let's first identify, do we have two chiral centers here? Yes, we have two chiral centers. We have this one and this one, meaning that this molecule qualifies to be a meso compound. But now, before that, try to identify again if you are able to draw a line of symmetry. First, we've seen that we have two chiral centers, and now try to see if you can draw a line of symmetry. Okay, now line of symmetry, the way it is looking as though you can be able to draw the line of symmetry there. But is this going to be possible? Let's check. Yes, it is going to be possible, because you have this bromine which is pointing at you. On the other chiral center also it is pointing at you. This hydrogen is pointing away from you, this other hydrogen also is pointing away from you, and also you have that methyl there. So that means this molecule is simply a meso compound, because it has a line of symmetry, or internal line of symmetry, and also it has same constituents on each chiral center. That means it qualifies to be a meso compound. So this one, it is a meso compound as well. It is a meso compound. Let's look at this other one here. So if you are to look at this other one, you are going to realize that it is also a meso compound, because you can simply draw a line of symmetry here, and this part can flip onto the other part equally. Therefore, you can say that this is a meso compound. And also you have these two chiral centers, and on each chiral center you have the same constituents, okay, or same attachments, meaning that it qualifies to be a meso compound. You've seen that you have a chlorine pointing at you, chlorine pointing at you, hydrogen away from you, hydrogen away from you, meaning that this can easily flip onto the other one equally. All right, let's have this one. Now, when you look at this example here, you are going to realize that let me even put another one there so that you can see. Let me put a BR here so that you can see. Now, if you are to look at this compound, you are simply going to find that this compound, by looking, you can simply say that it is not it is a meso compound, but you cannot just go direct and say it is a meso compound. First, look at the attachments. Number one, is this compound having two chiral centers? Yes, it is. This one is having chiral center. This one also is a chiral center. What is a chiral center? A chiral center is an atom having 4 different atoms attached to it. So here you have this, which is this, and that. Okay, so you have a methyl here, a hydrogen, and a bromine. Here also you have the same bromine, hydrogen, and a methyl there. So now, are you able to draw a line of symmetry here? The way this molecule is, you cannot be able to draw that line of symmetry. Why? Because you are going to find that this bromine here is pointing at you. Or let me start with the hydrogen. This hydrogen is pointing away from you, but on the other compound, it is pointing at you. So if you are to flip this one onto this, they cannot fit each other equally. Okay, because this one is pointing at you, this one is pointing away from you. So you cannot flip them and fit each other equally. Atoms can only fit on each other equally if they are all pointing in the same direction. So if you see that this one is pointing at you, this one is pointing away from you, these cannot flip on each other equally. Also, you've seen on the bromine that this one is pointing at you, but this one you don't know exactly where it is pointing because they have not given you the stereochemistry of that particular atom. So you don't know if this one can flip on that one equally or align with that one equally. So for this one, you cannot directly say that it is a meso compound. But since these are single bonds, when you see that they are single bonds, you can try to rotate. So what you do is that try to rotate this molecule. So what you can do is I can rotate this, I can keep this side of the molecule the way it is and rotate this part here. So if I'm to rotate like this, if I'm to rotate this bond here, it means that I'm also disturbing the atoms attached to this particular bond. So what will happen is that if I'm to rotate it, meaning that I'm trying to change the position of these atoms, you would find that if this hydrogen is pointing at me and I'm rotating it like that, meaning that I'm removing it from it pointing at me to it pointing away from me, because I'm taking it behind like that. So this goes behind, and then this one which was pointing away from me, it will come, pointing away from me to come and point at me. And then this one which was not pointing in in that direction, it can come and point at me. So in other words, what I'm saying is that if you find a molecule like this and it has all single bonds and the attachments are the same, then the direction in which these atoms are pointing are different or is different. What you can simply do is to try to rotate the bonds if they are single bonds and if it is not in cyclic. So you come and do this. You can say, okay, I'm rotating this. So you do this, you write that, you keep this one the way it is, Br, and then you write the hydrogen and that bond there. Then you come, now we are rotating this bond here. So we are trying to rotate this bond and see how these bonds can be repositioned. So we are going to say, if I'm to rotate this this hydrogen here, I'm rotating it, I'm taking it to the other side. I hope you're able to see. If I'm to rotate it, meaning that it's going to move from it pointing at me, it will go to the other side of the chiral center there. So instead of it pointing at me, it will now point away from me. So it's now going to point away from me. So it's going to point away from me like that hydrogen. Then this bromine, since it is in that direction which is not known, I can rotate it in such a way that it will now come and point at me. So I can rotate it and it can come and now point at me like that. Okay, then this bond here, which was pointing at me, it can now go and occupies the position where where this bromine was. So what I've just done is I've just swapped. This one has gone in that position, then this one will come in this position where the hydrogen is, and this hydrogen will go in that position there. That's what I've simply done. So that's how I've rotated. So this one has come here, that one has come there, and then this one has come there. That's what I'm trying to do, in other words. Okay, so here we are going to have the BR. This BR is going to come here. So I've written the BR. This hydrogen has gone there, and this has gone there. That's what I've done. So meaning that the BR will come here, the hydrogen will come here, and now this bond here, this one which was pointing away from you, it is the one which will now go there, like that. So when you check now in this case, you can see that you can now be able to draw the line of symmetry after rotating, because when you draw a line of symmetry here, meaning that this can flip on this one. Let me use this other marker here. So you are going to find that this will flip on this one because they are all pointing in the same direction. This one also is going to flip on that one. Then this one also will flip on that one equally. And therefore, this molecule now is going to be said that it is a meso compound. So this one is a meso compound. So this one can only be a meso compound after rotation. Without rotation, it cannot be a meso compound. So please, when you find a molecule or a compound like this, which has single bonds and it has the same constituents or attachments on the chiral centers, but the stereochemistry is different. So here we had the two stereocenters on this compound, but the attachments were also the same. What were just different, or what was just different in this case, was the stereochemistry, the arrangement of those atoms. So that means, how can you now make those atoms face or point in the same direction so that you can be easily be able to draw the line of symmetry? It's by rotating that molecule first. So if you rotate the molecule, you are going to find that you are now going to end up having this, and then that becomes a meso compound. All right, so that's how you can simply do that. Now, after that, we come to this one. Here also you've seen that you can easily draw a line of symmetry. Are we able to draw the line of symmetry here like this? No, it is impossible. Why? Because we are going to find that this hydrogen is pointing, the hydrogen from this chiral center is pointing away from you, and the hydrogen from this chiral center is pointing, this is pointing at you, this is pointing away from you. So these cannot flip on each other equally. Then this one is pointing at you, this one is pointing away from you, meaning that they cannot also flip on each other equally. So you cannot draw the line of symmetry here. Now, are we able to rotate these so that we can take them like the way we've done on this other question? No, we cannot be able to rotate. So whenever you see that the atoms are in a cyclic atoms, or atoms in a cyclic, cannot be rotated, because rotating atoms in a cyclic, meaning that you are simply just destroying the bonds, because you cannot, these, yes, they are single bonds, but you cannot rotate them on a cyclic. Rotating something on a cyclic is just simply equal to destroying the bonds on that particular compound. You cannot rotate this. When you try to rotate this so that it comes in this direction, you are simply just destroying this bond which is here. You cannot, you are actually trying to destroy the cyclic shape. It will no longer be a cyclic, but something else. So you are actually breaking the bond on that compound. So if you find that you have same attachments on a cyclic but different orientations of the atoms, then this compound cannot be a meso compound. So this one is not a meso compound. I've explained the reason why. So basically, that's how you should be able to know if a compound is a meso or not. Thank you so much for watching my videos. Kindly subscribe so that whenever I post any video, you are notified that I've posted videos. Thank you so much. See you next time. Bye bye.